Amigos de Data Evolution, y continuamos aquí en IOTA 2025 y tengo el orgullo y el placer de platicar el día de hoy con el doctor Alfonso Ortega. Él es un especialista en ingeniería mecánica, tiene un doctorado en Stanford de todo lo que tiene que ver con temas de térmicos. ¿Es correcto, doctor?
Sí, de termodinámica, de transferencia de calor, del flujo de fluidos. Y ahora todos mis esfuerzos están en el campo de data centers.
Bueno, es un placer y muchas gracias por el tiempo. No fue tan sencillo poder abordarlo. Hemos estado aquí en 3 diferentes charlas escuchándolo y bueno, el día de hoy queremos platicar un poquito de todo lo que tiene que ver con los temas que estamos viviendo direct to chip. El enfriamiento en todo lo que es la carga de trabajo, el workload de inteligencia artificial ha cambiado la forma en que se transfiere el calor. Y para iniciar quisiera platicar un poquito con el doctor Ortega sobre, o Al Ortega como es conocido.
Sí,
Al,
a todo el mundo.
Al, sobre le llaman densificación. What's the densification?
Densificación. Densification se refiere, les voy a platicar en inglés. It refers to the idea that the power and the GPUs that are currently dominating the conversation about artificial intelligence have to be physically very close to each other, because the different GPUs have to communicate with each other, and so there's something called latency. Latency is how long does it take for a signal to be transmitted from one location to another location. So to get the kind of speeds that we need in computing for training and then now inferencing in artificial intelligence, we require a very, very low latency in order to be able to reach the speeds that are required in order to be able to do these kinds of computations.
Okay, y for this computation, o lo vamos a hacer ahora en Spanglish todo esto, para poder hacer la transferencia de calor, se hablan de 3 tipos de sistemas: direct to chip, que hoy se habla de one phase y two phases.
Exacto.
Me gustaría entenderlo y conocerlo más para poderlo transmitir a la gente. Immersion cooling, que es otra forma a través de un líquido dieléctrico que existe. Y muchos no están de acuerdo que lo sea o no, la puerta trasera, ¿no? The rear door exchange.
Heat exchanger.
Heat exchanger. ¿Cuál es la mejor forma de poder incrementar el high power computing?
Well, there is no best practice right now, but it would be useful to understand one thing. We have reached an era where air cooling is no longer sufficient for high power, very dense electronic systems. So we've reached the end of the road for air. So now we have to consider data centers that are going to have liquid. So right now we are in the beginning of this new era, and that new era started by the companies, the data center operators, builders, accepting that they have to bring in water cooling infrastructure into the data center. So that's called single phase direct to chip. It is the easiest transition to liquid cooling. This is why we now see it starting to be adopted, right? So single phase direct to chip is using water plus ethylene glycol. It's called propylene glycol. It's called PG25, 25% propylene glycol in water, basically antifreeze in water. So that water passes through devices that are called coplates, usually made of copper, that you put on top of the GPU or CPU. You attach it through a thermal interface material, and then the heat from the GPU, CPU gets transmitted through the thermal interface material into the coplate, and then it gets transported out by the water. So this is now what you're starting to see. So right now, when you're talking about liquid cooling, what we're talking about is water cooling. So this is the first phase of what's going to be a continuation of advanced technologies. So there's a competing technology. The competing technology is single phase immersion cooling. Single phase immersion means that you take your electronic appliance, server, and you put it directly into the fluid. So obviously you cannot use water for this. You have to use a dielectric fluid. So typically a dielectric fluid like PAO, polyalpha olefin, an oil, thin oil, that is filling a large container, and then the electronics go directly into this tank, and then they are in direct contact with the fluid. And this is the way you get very efficient cooling in not only the high power components, but also the low power components. So right now there is not a competition, but there is sort of a world where we do not know whether the deployment into complete liquid cooling is going to be direct to chip or immersion. I think there's going to be both. I think that there's going to be niche markets that will definitely like immersion cooling. However, my own belief is I do not see immersion cooling finding its way into hyperscale data centers of the kind that are operated by the biggest companies. I don't imagine a future where you would have an enormous data center hall filled with immersion tanks. There are too many logistical issues related to handling vast quantities of liquid in open containers. There's also issues related to the compatibility of the materials with these kinds of oils. But there are a lot of users. For example, the immersion cooling has taken hold in the crypto mining business. Almost all crypto mining data centers are immersion cooled. So it's a really important niche market. It's a big market for immersion cooling, and this is where it's being tried out right now. So if it's successful in that niche market, it may find further acceptance in the large, hyperscale colo market, which is the really, really large market for data centers.
So do you see more the immersion cooling for data centers below 1 gigawatt of power?
Yes.
Or above?
Yes, most likely. So right now, there is a very large discussion about the 1 megawatt rack, the 1 megawatt rack, and the 1 gigawatt data center. That is kind of like the new future of the data center market. That's going to be the target, right? We're going to get to the 1 megawatt rack for AI computing, and we're going to get to a 1 gigawatt data center. So in my work, in my laboratory, we investigate things like limits. One of the things people ask me all the time is, what are the limits? And right now I cannot see that single phase immersion cooling will be able to handle a 1 gigawatt rack, but we definitely can handle it using direct to chip with two-phase cooling.
With two-phase, well, we have a lot of questions, but the two-phase cooling system, do you have any use cases that you see coming in the near future compared to one phase? What is the use case?
So right now the two-phase direct to chip is still in the laboratory. Right now it's in my laboratory. So right now I cannot say that we now have a market for two-phase direct to chip. Right now it is in the laboratory. It might be in a few deployments, but not many. There are not many deployments of two-phase direct to chip right now. Let's face it, working with refrigerants and two-phase is more difficult than working with water single phase for various reasons, but the obvious reasons is you're working with water. Well, we know how to deal with water. But in the case of refrigerants, we're working with fluids that now need to be contained. They're also at higher pressures. And so that there are other things that make it less ready for market, right? So there are not many use cases right now for two-phase direct to chip. It is primarily in the laboratory now. There's a couple of companies in the US at least that now are developing products, two-phase cooled racks, and those companies right now I think are in their infancy. And I think everybody is really asking the same question: is there a market for that right now? I predict there will be a market. It's just that the market isn't there yet.
Okay. For instance, if we have racks over, let's say, 45 kilowatts per rack,
Yeah.
uh,
Yeah.
we need liquid cooling, correct?
Absolutely. So, yes. So, 50 kilowatt rack is difficult to cool with air, almost impossible to cool with air. So, I think that is the transition where we found ourselves needing to transition to water cooling, liquid cooling. Right.
And what about the rear door exchange heater?
So, that's a very good question. So, let's be clear about one thing. If you use direct to chip single phase cooling, you're placing the cold plates on the hot components, on the high power components. But there's still a lot of low power components. And the low power components may contribute another 20% of the total heat load from a typical data center. So how are you going to manage the low power? The low power will probably be managed for a while with air, especially because remember, we have air cooling infrastructure in all data centers. And so the transition path is going to be how do we adopt two-phase or single-phase direct-to-chip in our existing infrastructure? And one of the things you can do is put a rear door heat exchanger on the rack, which is water-cooled. And so now you can use the room air conditioning to remove the heat from the low-power components, but it gets absorbed in the rear door heat exchanger. And so your entire movement of heat out of the white space, out of the data center hall, is in liquid. It no longer is transported by the air. So
it's a hybrid system.
It's a hybrid, definitely. It's a hybrid air plus liquid system. But this is a very efficient system because all of the heat transported out of the white space is in the water now. It's in the liquid cooling, not with air. So it's a very, very efficient system. I think you will see those kinds of deployments in the very near future. You'll start to see this will become kind of one of the standard deployments. Single phase direct to chip plus rear door, single phase rear door heat exchanger.
So that's the right mix for the next couple of years.
Oh, I think it's more than a couple of years. It's probably for the next 4 or 5 years, possibly, right? I think there will be investment in this rear door and investment in direct to chip, and you'll see racks like the NV72 racks from Supermicro and Dell and others. You'll see these becoming commonplace, and they will be the next generation of primary rack infrastructure.
Awesome. Do you think there's a standard available today for liquid cooling? I try to find something and no encontramos nada sobre standards of liquid cooling.
So the two places. So there's the question: is there a standard for liquid cooling now? No, there is no standards, but there are recommendations, primarily from two organizations. One of them is ASHRAE. ASHRAE TC 9.9 is a committee whose charge is to establish standards for thermal management in data centers. And they are very much providing guidelines, not standards, but guidelines for liquid cooling. A good example is a guideline for what is the highest velocity you can push through a pipe or a heat exchanger or a cold plate. At some point, the velocities get to be so high that they will start removing metal from the wall. That's called the erosion limit, right? So a good example is ASHRAE has established some kind of a standard for the highest velocity that should be tolerated within a system, right? That's a good example. The other organization that is doing a good job of establishing some guidelines is Open Compute Project, the OCP, which was originally founded by Facebook, right? Again, they're not establishing standards, but they have working groups,
best practices
and working groups. But I can't say that they're establishing what you would call a standard.
Okay, awesome.
Yeah.
You spent some time talking today about paradox. What is the paradox for high density or densification?
Yeah, the paradox is as mentioned by our panel leader today, Jackie, is Well, suppose we improve our system. Suppose we learn how to deal with these very dense systems, these highly dense racks, one megawatt racks, and we successfully engineer them and we deploy them. They will consume resources, right? And if we do it efficiently, they will consume fewer resources. So one of the things that I work on is how do we make sustainable IT? How do we make sustainable compute, right? Um, the paradox is the denser you make it, the more efficient you make it, the cheaper it will be, and then the more people will want to use. So the paradox is even if we make things more efficient, even if we make things say denser, more efficient, and so forth, it will. And one of the end goals is to reduce consumption of natural resources. It's a paradox because as soon as we do that, everybody will want more, right? There's this sort of insatiable appetite for compute, right? We have become addicted to uh, what compute does for us, right? It allows us to use our mobile phone.
Mm-hmm.
It allows us to listen to our Spotify. It allows us to send text to each other. It allows us to do everything, in Chat GPT seamlessly. We expect it to be instantly available 24/7, right? That's what we expect. In a sense, we become addicted to it. So the paradox is, if we make things more efficient, you know, basically people will just want more and more. So it's paradoxical, right? That's, I think, one of the things that Jackie was pointing out is this concept.
Yeah, that's one of the key questions I guess we have for all of us. What's your vision for the next 5 years, and what is your recommendation, not for hyperscalers, which is the big data centers, but
Mm.
for, well, Latin America, we have different types of data centers below 10 megawatts. Uh, what is your recommendation when they have to make an assessment? What type of solutions for air conditioning they have to use? What do you think is the best way to analyze what is the problem, what is the need, and how to think what is the best option available? Because there's a lot of confusion right now. What is the best solution if we have to install or implement a air solution, or we have to, because this is a lot of money, the capex for air
Of
conditioning,
course,
and it seems to be it has to last for 20 years or
yeah.
it's between 15 and 20 years. And a lot of companies are concerned about how do we implement or how do we invest in air conditioning solutions for thinking about AI within 5 years is going to change a lot or not. What is your recommendation for the average data center?
That's a really big question. I'm not sure I'm equipped to provide you a very good answer. But obviously, the place you start is what is it that you're doing with that data center, right? Are you developing a data center to do AI computations, or is your data center a mid-range data center to provide colo services?
Concern.
Is it to provide storage? Is it to provide mid-range computation,
Mm-hmm.
cloud services, credit card transactions? Um, what is it designed to
So
do?
define what is the need,
What is
right?
the need? What is the market for your data center, right?
Mm-hmm.
Um, Obviously, the main drivers for this liquid cooling right now are
Mm-hmm.
very, very high-end machines. I- I- Look, here's the way to think about it. Right now, we're starting to see that mainstream colos and hyperscale data centers are now doing things that used to be done on high performance machines, HPC, high performance computing, right? So what we're seeing is that what traditionally was this market for high performance computing, which was kind of a niche market, right? It was for doing very, very high end mathematical computations, right? We're now seeing those kind of workloads migrating downwards to traditional service providers that are providing now AI assisted services like
Mm-hmm.
ChatGPT,
Mm-hmm.
right?
Yeah, correct.
And so now the workload of a, shall we say, a traditional data center is now resembling the workload of a HPC of the past, a high performance computing in the past, right? So if I'm building a data center, well, I would have obviously I ask myself, well, what's my market? Am I providing high performance, computing for customers, or am I providing colo services for a company or a hospital or a university? Am I providing storage? Am I providing computing? Business services? Is it a enterprise, market? Companies, hospitals, universities, schools, or am I providing services that basically are high-end compute? Right. That's the question we should ask ourselves, because it's still two different markets. It's still two different things. Right. Right now, the hyperscalers and the high performance is still a relatively small percentage of the total data center white space in the country and in the world. It's not. It's what we hear the most about, but it definitely is not the majority of data centers. The majority of data centers are still providing these, shall we say, these low density applications, right? So if you're building a data center in Mexico, then you should ask yourself, well, who's my customer? Am I building it for a hyperscaler that is going to provide high performance computing, or am I going to build it for the traditional enterprise systems which are providing services for companies? That's the question.
That's a big question, and I guess we need to understand how we're going to answer that question.
Absolutely.
Last but not least, what is your vision for 2030 in terms of thermal management?
2030, what is that, 5 years from now?
5 years from now.
Yeah. So. I think 5 years from now, you will see that water cooling is completely deployed. See, the biggest barrier, the biggest hurdle we needed to jump through was companies willing, data center companies, data center operators, builders, willing to put water in their data center, in the white space, on the floor. Okay, that's a huge, huge barrier. I've been in this business for 40 years. We've been talking about liquid cooling my entire career. This is nothing new. Believe me that the technology is not new. Okay, so we have been, in a sense, waiting for liquid cooling to eventually be adopted. Well, we have arrived at that moment. We have arrived at that moment about 3 years ago. Right? So that was the big hurdle to get through. So I think in the next 5 years, what we're going to see is the rapid acceptance of best practices, good systems that don't leak, systems that do not produce corrosion, that are compatible with materials, etc. All the nasty problems that you have to deal with in real engineering systems, right? That's what's going to happen in the next year or two, and we're going to start to see very large-scale deployment of water cooling. Okay, we're also going to see the continuing increase in rack power density. Right, we're going to reach 100 kW. We're going to reach 200 kW. We're going to reach 300 kW. And there's going to be like two different paths. One of them is the high performance path, right, which is going to be the machines that are used for AI, right? And then there's going to be everything else. So this is what I see in the next 5 years. I'm seeing that the hyperscalers and those data centers that are servicing high performance computing, they're going to be the ones that are leading the way on adoption of advanced technology, water cooling to start, and then also investing in the next thing, right? What's going to be the next thing, right?
All right. Thank you. Bueno, este es parte de lo que tenemos hoy con el doctor Alfonso Ortega. Al, muchas gracias por la oportunidad.
Sí, con gusto.
Y estaremos en contacto con él. No se pierdan toda la entrevista y tendremos alguna oportunidad de platicar en algún webinar próximamente.
Ok. Muy bien, muchas gracias.
Muchas gracias y gracias a todos ustedes. Hasta la próxima.